Hi, I'm Carla Westfall from Saddleback College again, and here we're taking a look at another limit of an indeterminate power. To see that it's a determinant, notice that the base is just a rational function. As we go off to infinity, rational functions are going to be dominated by the fraction of the lead terms. So the base behaves like x over x, which is just 1, and then x squared is going off to infinity. So we've got an indeterminate form of the type 1 to the infinity. So I'm going to do what I do with all indeterminate powers. I'm still taking the limit here. I'm going to give myself a little bit of space. Right, that I've got x plus 1 over x to the x squared. In order to bring that x squared down, I'm going to take the natural log of this expression. But I know that that changes it, so I'm going to undo that by exponentiating. That way I've done something and then undone it, so I haven't actually changed the value of this expression at all. And of course the reason I did that is so that I can use rules of logs to bring that x squared down in front of the log. So now we've got the limit as x goes to infinity, exp of x squared natural log of x plus 1 over x. Now I really want this limit next to this piece right here that's in brackets because that's where all the x's are. And the exponential function is continuous. So I have a rule that says that I can bring that limit inside provided I get something that makes sense. That's going to mean provided I get a number, because the domain of this exponential function is all real numbers. So as long as I get any number, I'm okay doing this. So I'm going to go ahead and hope that it works. Oops. Natural log of x plus 1 over x. I'm just going to make a note here that this step right here is legal if the limit is a number. If it's not, then this step was not allowed and we're going to have to come back and adjust things. Okay, now I'm hoping that at this point we should have an indeterminate product. X squared is going off to infinity. We said our fraction here was approaching 1 and the natural log of 1 is 0. So we do have an indeterminate product. So we convert our indeterminate product to an indeterminate quotient. The more complicated factor was this natural log of x plus 1 over x, so I'll keep that on top, but instead of multiplying by x squared, I'll divide by its reciprocal, 1 over x squared. No negative sign there. So this should now be an indeterminate quotient. The top is going to 0, and the reciprocal of x squared will also be going to 0. So at this point, we can go ahead and use L'Hopital's rule. So we have exp of the limit as x approaches infinity. Now when I take the derivative on top, the derivative of the natural log function is just the reciprocal function, so I'll flip that fraction, x over x plus 1, and then I need to use chain rule, so times the derivative of this inside part. To make the derivative of the inside part a little bit simpler, I'm just going to distribute that division by x. So I'm going to write this as x over x plus 1 over x, and then I'll come back in a moment and take that derivative. On bottom, the derivative of 1 over x squared is negative 2 over x cubed. Okay, so this is exp of the limit as x goes to infinity of x over x plus 1 times, now x over x is just 1, the derivative of 1 is 0. 1 over x, the derivative there is going to be negative 1 over x squared. And then all of this was over negative 2 over x cubed. So now I'm just going to simplify this fraction. Rather than dividing by what I have on bottom here, I'm going to flip and multiply by its reciprocal. So we'll have exp of the limit as x goes to infinity of x over x plus 1 times negative 1 over x squared times negative x cubed over 2. Again, just multiplying by the reciprocal of that fraction that I have on the bottom. So I can see my two negative signs here are going to cancel. And it looks like I can cancel two factors of x as well. So that x squared will cancel, and then I'll have 2 of those x's canceling, so I'll be left with just 1 factor of x here. So that takes me to exp of the limit as x goes to infinity. X times 1 times the 1 left over x is x squared, all over x plus 1 times 2 is 2x plus 2. And at this point, we can see that we have a problem, because now this limit is the limit of a rational function as we go off to infinity. It's going to be dominated by the fraction of its lead terms, but x squared over 2x is going off to infinity. And if you remember, way back over here, we said that we were able to pull the limit inside that exponential function if we got a number. We did not get a number, we just got infinity. So I'm not actually allowed to write this. Writing this is just as much nonsense as writing e to the infinity. Can't do that. I can't plug in infinity. But all is not lost. So what I'm going to do is I'm going to say, okay, I'm going to cross off this exponentiation. All of the work that I did in evaluating the limit of the log was okay. I just wasn't able to actually pull that limit inside. And I can't plug it into the exponential. So I'm going to erase that equal sign. It's no longer equal to what I have on the line above it. The line above it was the limit of this power. Now, starting on this line, I'm taking the limit of the log of that power, which is different. But the limit of the log of that power is infinity. And all of this work is perfectly valid in saying that the log of x squared plus x plus 1 over x to the x squared goes off to infinity. So now what I want to do is actually evaluate the original limit, and I can do that. All I'm going to do is change variables by making a substitution. So I'm going to say that this piece right here, I'm going to call that u. And we've just determined that as x goes to infinity, u also goes to infinity. So I can take this limit, and I can say this is now the limit as u goes to infinity of exp of u, or the limit as u goes to infinity of e to the u. I'm not literally writing e to the infinity, but I'm indicating that I'm looking for the behavior of the exponential function as the input gets really, really big. And just familiarity with that graph tells me that as the input to my exponential function gets big, the output gets big too, so that this limit will be infinity. So, if you try to pull the limit inside, and it turns out not to be legal, that's okay, just adjust your notation. You can keep the work for evaluating the limit of the log, and then just exponentiate at the very end. All right.